special redshift in the universe, means especially in the low redshift region, and if you can find out those special redshift, and if we can measure the Hubble parameter at those special redshift in a kind of a model independent way, and if you can do that, comparing with the Planck, if they are consistent with the Planck or not. The idea is basically, Frank, that already in the from the DESI results, people have shown with some particular parameterization that there is a sort of evidence from dynamical dark energy or deviation from the lambda CDM. So we try to find out if there is any special redshift in the low redshift regime which actually is driving this deviation from this lambda CDM. And in doing so, we also use the same technique for the growth data that I will describe, and it allows us also to measure the growth factor directly from the background quantity. Usually it's difficult to measure the growth factor because it comes with the bias. So instead we usually measure the redshift space distortion parameter, F sigmoid, and this also needs the information from the sigmoid. So here we will show that it may be possible at some very special redshift that one can measure the F or the growth factor directly, and it may help later on if you can measure the 21 centimeter power spectrum or others in that specific redshift. One can get the information for the bias also. Okay. So it's very quickly that after Planck 2018, we know that the lambda CDM model is one of the best model. It actually fits very well the Planck data. Not only Planck data, the data at that time available, the BO and the supernova data, and it's mostly driven by these three parameters, at least at the linear level of fluctuation. But recently, not recently, I think another last 4 or 5 years, there are two problems with this lambda CDM. Everybody knows, I will not go very detailed, that there is the Hubble tension. The one Hubble parameter is measured through the history of the physics of the early universe, which needs a cosmology, and Planck assumed this lambda CDM cosmology. And the other is basically measured from the astrophysics of the stars by this Schu's measurement, and they are roughly deviating by 10%, around 5 sigma, fine. Still we don't know whether this tension will actually the tension or there is some systematics involved, but in time maybe we'll know it better. Also now we have these results from the DESI DR2, assuming a sort of a deviation from the lambda CDM, parameterizing through this kind of parameterization, and it actually gives the region, allowed region in the parameter space, which is very, very far away from the lambda CDM. I mean, more specifically around 4.2 sigma or 4.3 sigma. And taking different combination itself is actually this results is quite robust. Note that deriving this result, there is no assumption of this Schu's prior. So this result is not driven by the Schu's prior. This is there in the DESI data and all other data, but the question is that is it really a new physics beyond the lambda CDM, or this is just sort of a artifact of the CPL parameterization. People are doing this thing. There are a lot of papers just to try to see that with different parameterization or different dark energy model, whether these deviation from the lambda CDM is still existing or not. Fine. So we'll try to do it, but in a sort of a different way. So this is just the basic equation that we know for the background cosmology. Let's say for the timing we are concentrating on the background cosmology, and they are mostly we have these two observable. One is the angular diameter distance. We measure it through the BO or the CMB acoustic scale, and then there is the luminosity distance that we measure through the supernova flux. Fine. And the idea is that what we do, we just assume a equation of state for the dark energy like CPL parameterization. We go through all those things, calculate the H, then calculate dA, dL, and with the data we just constant the parameters of this equation of state. Fine. Our idea is to go backward, that from the data directly, because the data are available in DL and DA, so we really try to reconstruct this DL and DA independently, and then go back. As you can see that here in this equation, if I go back, I can reconstruct the H. And from this equation, this is the the pressure of the dark energy. If the pressure of the dark energy is not constant, then gives you a very strong hint of that whether the dark energy is a lambda CDM length cosmological constant or not. It cannot give you directly the what kind of dark energy, but it can at least gives you the information that whether the dark energy is a cosmological constant or not. And for that, you don't need any information from the matter, because most of the time doing this way you need the information from the matter, but going this way just from here we don't need any information from the matter. Fine. So what we do, let's say angular diameter distance. So the Hubble parameter is related by the angular diameter distance with this angular diameter distance and its derivative. But can we do better? Is it possible to get the information of the Hubble parameter just from the distance itself without taking into account the derivative of the distance? Fine. So let's plot this angular diameter distance. So this is the angular diameter distance, and always this angular diameter distance peaks at a point at some redshift. Fine. And if you plot the derivative of the angular diameter distance, remember that they are plotted in the defined scales. So this is a redshift where these two values are actually equal. Okay. So there are two redshift, special redshift, where the angular diameter distance maximizes, and a redshift where the angular diameter distance is equal to its derivative. Okay. So if you take this thing, so at where the angular diameter distance maximizes, so then at that point dA prime is 0, so h is directly equal to the angular diameter distance. And when it is crossover, means the distance and its derivative crossover, then the Hubble parameter also related directly to the angular diameter distance, because I can replace dA prime by dA. Fine. So there is at least two redshift where I can get the Hubble parameter directly from the angular diameter distance. Fine. But I can do more. Fine. I can use now all other distances like the dl or dm, their derivatives, and I can actually have 7 redshifts where these derivatives are equal to the distances. So actually we can get 7 redshifts. The redshift 3, Z3 and Z7 is basically the angular diameter distance derivative, and it's equal to the derivative. And the others are actually coming from the distances of the luminosity distance or other. So there are 7 redshifts where I can actually get Hz directly from this dA parameter. Fine. So this is for the background. Fine. Now let's see what happens to the part of the universe. Fine. In the part of the universe, I have this matter density contrast. This is the growth factor. As I said, that we cannot directly measure the growth factor. What we measure is the F sigmoid, the redshift space distortion. This is driven by this equation. But now if you plot the F sigmoid also maximizes at some point. This we have plotted with the Planck lambda CDM base fit, but it also has a maximum value. Fine. Now we constructed a diagnostics like this. So as you can see, this quantity Ez is h by h naught, W is the dark energy equation of state. These are background quantity, but the F is sitting over here, the growth factor. Now the interesting fact is this Sz, that where it maximizes, this Sz is actually identically 0. So as Sz is identically 0, I can actually get at least this redshift, the value of F, just from the background quantity. So I can constant the background quantity very, very accurately from defined data, and at least at this redshift I can get the growth just from the background quantity. Okay. So this growth factor can also be determined just from the background quantity at this z equal to z max. Okay. So these are the ideas. So now let's use this defined data and just to see that what is happening. Okay. So this is the work that I worked with Purva sitting over there. So we take defined data, the DESI data supernova, the DESI data, and also we fix this is our pair that we fix the acoustic scale or the distance to the last scattering surface as given by the Planck value. Fine. So we are not assuming any early dark energy or any modification of the early physics. So we are fixing that this acoustic scale is fixed as given by the Planck. So that is our sort of you can say an anchor. Fine. So these are the data, and what we did, just we basically reconstruct the moving distance and its derivative, and from that I can reconstruct the dA, dl and their derivatives. Actually we reconstructed the dimensionless distance, which is this, for all these distances, and then we can reconstruct the E, which is the h by h naught. Okay. So that is the program. Now there is two reconstruction program that we use. First we use this multitask Gaussian process. We use defined kernels and reconstructed this value and get this 7 redshift point. Once we get this 7 redshift point, what we did a knot-based spline method. So we take the knots at the 7 redshift point and do a spline for order 3rd order or 4th order or 5th order, and again reconstruct this thing and see that whether they are actually consistent or not. Fine. So that is the program, the data, and this is the reconstruction program. Fine. So these are the reconstruction. I am showing it for just one kernel, but all the kernel that I have used here, that I mentioned, there are 4 or 5 kernels, the results are completely robust and they are absolutely similar results. Okay. So these are one reconstruction of the dm prime and dm double prime. This blue is our reconstruction, is red is basically the Planck. So as you can see that they are already showing some sort of difference from the Planck. And these are all these distance and their derivative and all these 7 redshift points that we have can get from here. And then once we have the 7 redshift point, we get the dA, those redshifts that I showed earlier, and also the H or E by, H by H naught at the 7 redshift points. So what is the result? So this is the results, fine. So these are the 7 redshifts that we have. These and these are basically that I mentioned. This is basically where dA prime equal to 0, and this is where dA equal to dA prime. And these are other redshifts, means like where the dA is equal to dL prime, dm equal to dm prime, and so on and so forth. Fine. So these are the 7 redshifts. These are the values of dA from that 7 redshift that we have. These are the Planck values that we can get from the Planck chain. So these at these redshifts for this dA. At the dA, the tension level is basically this, fine. And then we get this reconstruction E that I showed over there, that how you can get H, and then H, H by H naught you can get E. And these are the value in E and E Planck. And as you can see, the tensions are quite high, fine, around 5 sigma kind of tension at these 3 redshifts. And if you go to higher redshifts, these results going exactly to the Planck, fine. So at redshift like more than 1, practically there is no tension. So it actually shows that these are the kind of a redshift regime where there is a tension, there is some sort of a strong deviation from the lambda CDM. But as you go beyond that redshift, more higher redshift, the things go smoothly to the Planck value, fine. This is for this multitask Gaussian with that one kernel, and as I said, all the results are similar to different kernels. And this is when you do this knot-based thing, that you take these 7 redshift, you take the 7 redshift, take them as knots, and then you spline kind of thing. So here we did the 3rd order, means cubic spline, 4th order spline, or 5th order spline. The result I am showing is for the 4th order spline, but the 3rd order spline or 5th order spline, they are also the similar results. And as you can see, the behavior of this thing is basically same like as I showed for the Gaussian process. And again, the tensions are little bit less because the error bars here are a little bit higher, but the pattern continues. That at the high redshifts, at the low redshifts, around redshift 1.3 to 0.5 or something, there is a strong tension with the Planck thing. But as you go to the higher redshifts, these things actually goes to the Planck results. Fine. So these actually sort of encourages us that. And as I said, that here we have not used anything like Schu's measurement, so everything is Planck prior. So within the Planck prior itself, at this redshift, as you can see, there is a strong anomaly with or tension with the Planck values. Fine, that is there in the data, and the results are quite robust. Whatever way the reconstruction you use, at least here, the defined Gaussian in the Gaussian process with defined kernels, or the knot-based process with defined orders, all of them give you the same kind of results. Fine. Now these are the reconstruction that define the rho dark energy, the pressure of the dark energy, and the null energy condition. Okay, this is the null energy condition. And as I said, that from here the pressure constant is not consistent with our reconstruction. There is a 2 redshift regime around here that I already showed, and here that there is a strong deviation from the constant pressure. For the null energy condition, there is an indication that there is a violation of the null energy condition, so it just goes to the phantom. But okay, the error bars here are very big because we don't have many data beyond redshift 1, so we cannot constrain that much. But at least for the low redshift, things are consistent. I mean, it is not cosmological constant, fine, but it is consistent with the null energy condition. So the results are more or less consistent what people get with the CPL parameterization. So now let's see that how what happens with the CPL parameterization. Let's say you have the CPL results with the CMB, all these chains, you do the same thing for the CPL and compare with us, fine. So this is the results, fine. So this is the Planck numbers. The red points are basically the Planck numbers at this 7 redshift, fine. And the blue points are our knot-based reconstruction, and the green points are basically the CPL chains that we use with the Planck DESI DR2, Planck CAG DESI DR2 and the DESI DES5. And as you can see, these 3 redshift points that we have, that I shared, that there is a strong constraint or strong tension from the CPL thing, the exactly same thing happens. So our results is completely inconsistent with the CPL, and in a sense that it actually also says that whatever we are getting from the CPL things are more or less the same, is robust, because we are completely model independent reconstruction. And most probably the tension or the deviation from the lambda CDM which is there in the CPL, they are actually driven by these three redshifts, or the HZ at these 3 redshifts, fine. So, and now as you can see that the EZ, so this is our reconstruction for the EZ, and this is the CPL. This is the reconstruction for the DM, and this is for the CPL, fine. Deviation from the lambda CDM, and our results and CPLs are actually quite consistent, fine. There is an interesting thing, as you can see over here, this E has a sort of, or the H has an increased value from the lambda CDM around this redshift point where I was showing, and the DM is basically has a minimum and again going that. So it actually showing that if you look at the supernova, or let's say you have a lot of supernova here, what it actually predicts is that around this redshift, the DM is actually going down, so you start getting this supernova looks brighter than what the Planck actually predicts, but this brightener, being the brightness of the supernova that is brighter, it actually attains at some redshift maximum brightness or maximum brighter, and then again it reduces. So there is a non-trivial Z dependence of this deviation from the thing, fine. It most probably may not be sort of addressed to some systematics in the supernova. So there is a non-trivial Z dependency here, okay. So this we find is quite interesting. I have 1 minute, fine, maybe, okay. So and these are basically our forecast for the AP test. These are our numbers, and these are basically what we can get from Euclid. And as you can see, these 7 redshifts, the Euclid numbers are quite suppressed. So maybe if you do this thing afterwards with the Euclid number, so things will be more tighter actually. Okay. Just go to the now this F sigmoid that I showed over here. So we did this thing. This is a paper with Topomoy Guhasarkar at BITS Pilani and his student. So we did the same with the F sigmoid data. So there is 2 things we have done. We did only the SDSS data where we have around 5-7 data that we did, and also all the F sigmoid data that is currently available, fine. Interesting fact is that if you take the only SDSS data, nothing else, no supernova, nothing, you do the same DA and DA prime, that reconstruction, that DA prime is 0 and DA equal to DA prime, you get the same, exactly same redshift, okay, that's the thing. And at the 2 redshift, your EZ only in the SDSS has a 2 sigma deviation from the lambda CDM, and here there is no deviation, which is consistent with our result. But in the SDSS itself, at this redshift where DA equal to DA prime, you get a 2 sigma deviation without any supernova or anything, fine. We also, as I said, from this F sigmoid, the highest, I mean where it maximizes, we get the redshift, which is basically this for this SDSS data point, or all the full supernova data, we get this kind of value, okay. And then we can get the F value over here. As you can see, the central values are quite different, and the central value is smaller than the Planck value, which is also consistent, because we get this value around this region, H is higher. If the H is higher, there is a more Hubble friction and the growth will be smaller, fine. So that actually also showing over there that we get around this redshift 0.4, which is around exactly where we get the higher values, that the growth is actually smaller. For SDSS, obviously the error bar is big, so we don't get any any tension with the Planck. But if this value remains same with the DESI data, we can do it. Still now this whole DESI full shape likelihood is not released, but one can do it there. And if this value remains same, but this value get reduced quite a lot, then maybe some tension will also come over here. And once you get the F, I mean, you can use the 21 centimeter line power spectrum, you can actually get the beta parameter from the RSD, and then using this F, you can actually get the information of the bias at this redshift. Okay, so we cannot do that at this moment, but that can be possible because we can now get F measured at some particular redshift, low redshift, very accurately from the background measurement. Okay, so this is all that I want to share with you. So these are the conclusions. So I stop here and I can take questions.
What stops you from playing the game again and again? Like you said, at some point DA is DA prime. I can have a point that DA prime is half of DA.
No.
Or some numerical factor times DA.
You can do.
You just get an extra piece.
No, you can do, but if you do it, if you can do it, okay, where I go? You can take any value over there, but then where you go? Okay, let's see here. Yeah, so you say that, okay, I get dA prime from one part of dA, fine, and then some points over here, fine. But we tried that, I mean, it's like we are doing that, not only that, we can actually do the dA double prime also, okay. At this moment, the redshift that you get there, maybe the data are not that thing that you don't get meaningful constant from there at those points, fine. So, but that can be done, I mean, if we get those things.
Yeah, one very brief question. Where you see that, maximum deviation from Planck, does that depend on which supernova sample you
Okay,
use?
so we have currently used the DACE data, but we are now doing just check these results with Pantheon Plus and Union, but maybe we'll get the results very soon, but yeah.
Hi, thanks for a nice talk. So one comment at first is about the shoes calibration. So even all the high redshift DAs, Pantheon Union data sets are calibrated with shoes as from low redshift. So the mu distance modulus minus distance modulus fiducial is calibrated to a zero line, assuming shoes prior for redshift below 0.01.
0.1 or 0.1?
0.01.
Okay.
So the low redshift calibration is already done. So all these statements are assuming shoes calibration of supernovae for DES, Union and Pantheon. So that's the only thing they do, and then they extend it to high redshift. And
actually, I mean, this is the thing that also means FSSU also mentioned that there is a problem of calibration at the very low redshift, fine. And we did that, so we take this different of calibration, fine, and we actually get that these results are not much dependent upon this calibration. So let me, if I have the slide. Yeah, so what we did, like from the DES results, so we get a shift at a very low rate shift, this kind of shift that the FSSU has mentioned, and we did the redone the calculation, and we are getting around more than 3 sigma.
So DES samples have photo-z redshifts errors. If you consider the Pantheon, which is 1701 number of supernovas, you will see that the amount of departure you see from the results in comparison to DES Y5 is more.
Okay.
So Pantheon is more substantially contributing to the signal.
Okay.
You can calibrate it at a low redshift, but the in between redshift 0.5 to 0.7, there is a significant departure, which happens.
Okay.
This is a comment on the calibration. You can see one of the DAISY plots, which shows that there is an overall calibration error, which is they just subtract a number so that it looks like around 0. They said it's in the paper.
Okay.
Another point is about the omega matter. Omega matter is inconsistent between Planck 2018 Act later and
Assuming a lambda CDM model. Assuming a lambda CDM model.
Yes. So how do you include that?
No, but we don't need omega matter here at all.
No, but when you are fitting it, you will need at the anchor redshift values, the amount of omega matter density, whether it is going to lambda or not.
No. So see that what we are doing, we are having the dA or dL values, fine. So you are directly reconstructing dL and dA, fine. And from there, that the method that I mentioned, I can directly get the H. So I don't need omega matter here at all.
No, what I am trying to say is when you equate the two derivative with the dA, there are omega matter entered in that particular Z choice, right?
No. See again, I have this dA reconstructed.
You are just reconstructing at that
dA, fine, and then I can also get the dA prime from their reconstruction, fine, and then I just calculate H from there, fine.
So do not assume any value.
No, this whole exercise is absolutely independent of any cosmological parameters.
So then maybe it is going to a lambda because of the similar value of omega m, which
maybe, but in this exercise there is no omega matter dependence actually.
Any other question? Okay, if not, then let's thank the speaker. Our next speaker is Shantanu Desai.
Can you hear me or? Can you hear me or any? Yes, yes. Okay. Okay, so my original plan was just to attend this meeting, sit back, relax, and enjoy the talks. But I think Dheeraj asked me to give a talk, and again, the mid-semester has just started, and anyhow, so I've also had a very early start. So anyway, let's start with something very, very simple and very trivial, which all of you probably know it since your kindergarten. Okay, so what is this? This is a dark matter problem. You look at a rotation curve. The rotation curve is flat. Naively, what we expect from baryonic matter, from luminous matter, we expect a falling rotation curve. There's a rotation curve from disk, expected rotation curve from a disk, from a gas, and then we posit the existence of a dark matter halo. So this is ubiquitous across all galaxies. Okay. Now, if you ask a different question, which is there any common property for all galaxies for which the need for dark matter arises? In other words, is there any property like distance, mass, acceleration, velocity, angular momentum, whatever? Now, if you look at plots like this, if you show the plots to, let's say, someone who doesn't know anything about dark matter or cosmology, that person will say, okay, the need for dark matter arises maybe above a certain distance. Okay, so at small distances you don't need dark matter. At distances beyond a certain point you need dark matter. Turns out that is not true. You look at hundreds and thousands of galaxies. For every galaxy, the need for dark matter arises at a different distance. Okay. Now the first person, if you ask the same question in a different way, okay. What you can do is you can plot the dynamical mass over the baryonic mass. So if the dynamical mass is equal to baryonic mass or less than the baryonic mass, then there's no need for dark matter. If it is greater than baryonic mass, then you'll need dark matter. Okay, if you plot something like this, okay, unfortunately it's not coming, I don't know why this portion is cut off, but anyhow, I think I've sent a PDF. Anyway, let me just move over it. You'll see that the need for dark matter arises below a fixed acceleration scale, okay, 10 to the minus 8 meter per second square or 10 to the minus 10 centimeters per second square. Okay, so this is from an older plot, and this is again a rough analysis done by one of my undergraduate students. So basically you can see that the need for dark matter for all spiral galaxies arises below a fixed acceleration scale of 10 to the minus 10, 10 to the minus 8 meters per second square and 10 to the minus 10 centimeter per second square. Now another thing you can do, right, if you look at the rotation curves, if you take the velocities and you plot that versus the baryonic mass for which you model it from disk, gas and anything else, you see a nice empirical correlation. Okay, so the x-axis is the velocity, y-axis is the baryonic mass. You see a very nice correlation over 2 orders of magnitudes. Now again, naively, if you think about it, it's a little bit counterintuitive because for all dark matter dominated systems, I think dark matter constitutes about 90% by mass and baryons constitute only about 10%. So why should there be such a strong deterministic correlation between the total mass, between the baryonic mass and the asymptotic velocity? Okay, if someone told you that the dynamics of all planets in the solar system is governed by Pluto, you would say it's preposterous. Okay, but anyhow, so this is an observational fact. Another plot, can people at the back see the plots? Okay, okay, let me just go ahead. So in the 2009, it was shown by doing a core dark matter fit to a whole bunch of dwarf galaxies, spirals, elliptical. The dark matter surface density is constant. The dark matter surface density is the product of the core density times the core radius. I think this is by fitting a Burkert profile. You can do the same to other isothermal profiles. You can do an NFW fit, you get something like this. Okay. So anyway, so this is a little bit disputed by some authors, but let's just go ahead, okay? Finally, the money plot for all this is something called the radial acceleration relation. So the x-axis is the baryonic acceleration, and the y-axis is the total acceleration. You see this nice pristine deterministic relation between the total acceleration and the baryonic acceleration, which can be fitted by this non-linear function with very negligible scatter of about 0.1 dx. Okay, so in some sense, this relation subsumes all the other two or three relations I showed in the previous plot. Okay, so this is an observational fact. Okay, now I'll just make one sociological point. Okay, which is that I think David Merritt has a nice paper in a philosophy journal where he surveyed through 40 books, textbooks in cosmology, structure formation, dark energy, and only one of them mentions both all the facts which I mentioned in the previous slides. Okay, so somehow I think there's a conspiracy that what he claims is that there's a conspiracy that students should not learn about it. And some of these textbooks include, some of these authors include Steve Weinberg, George Ellis, I think Martin Bourgeois, who is one of the pioneers of loop quantum gravity. Also, I think it includes, Debashish Majumdar from Science Institute. Also, it includes the book by Hoyle, Narlikar, and Burbidge, which presents a contrarian approach to cosmology. But even they don't mention it. Okay, so anyhow, so that's the. So what do you do? So the first, I think, Milgrom first proposed a modification to Newton's law such that below this acceleration scale, below which the need for dark matter arises. Okay, here it's actually, okay, no, here it's coming out fine. Okay, he posited that acceleration goes as square root of the Newtonian acceleration. And so once you do this with one line of algebra, you can get the baryonic-Tully-Fisher relation. And in order to ensure a smooth transition between the two regimes, he posited this an interpolating function. So this modification to Newtonian gravity is called modified Newtonian dynamics, and it works remarkably well for galaxies. Now I should mention that Milgrom was not the first to propose a modification to GR to dispense with dark matter. Beatrice Tinsley did it in 1978. Joel Tolin did it in 1981. So they proposed 1 by R force law, but to the best of my knowledge, Milgrom was the first one who proposed a modification below this acceleration scale. Okay, so now obviously before you sort of grill me, there are lots of problems in MOND. MOND does not work for galaxy clusters. This has been known for a long time. I think much below the bullet cluster. I think Simon White was the first to look at it. You calculate the MOND dynamical mass using whatever prescription Milgrom gave, that it's still much greater than the baryonic mass. You can crank up A0 and you can make it agree at one point, but it does not agree at all points. And again, there's obviously, I think, if you attend any particle physics conference, people always show the picture of bullet cluster. I think that has been a little bit oversold, but anyhow. And the main argument against MOND is that it does not agree with the observed matter power spectrum. This was shown by, I think, yeah, just quickly. I'll get 1 or 2 minutes for this. Thank you. Okay, fantastic. I think I won't go through the plots again. I'll just. I think the beauty is in just staring at these plots. Okay. Oops, sorry. Okay. Now again, the main argument comes just with the observed matter power spectrum. It turns out that I think you'll get much more enhanced oscillations without the dark matter. Okay. Another very strong watertight argument comes against this relativistic Mond theory comes from GW170817. Okay, so I think in Subhadeep's talk yesterday he talked about gravitational lensing of gravitational waves. A corollary of that is that gravitational waves also experience Shapiro delay. Now you have heard must have heard many times that GW170817 shows that the speed of light is same as the speed of gravitational waves up to 1 part in something. It's slightly more nuanced than that. So that it not only tells you that the vacuum speed of light is same as gravitational waves, but also the line of sight Shapiro delay is same for both photons as well as gravitational waves. And that rules out a whole class of modified theories of gravity, which actually try to explain Milgrom's modified formula. So this includes Bekenstein's Tevez theory and few other theories. Okay, but I should mention that I think recently Skordes and Slosnik have come up with a new modified theory of gravity, which sort of explains the GW170817 and so on and so forth. Okay. Okay. So basically, so what do you do? Okay. So there are two ways to deal with this. One is, okay, you just you ignore all of these successes of Mond at small scales, which is fine, which is what many people do. Another one is you sort of ignore all these problems of Mond at cosmological scale and just say that lambda CDM is host. So this is what a small fraction of the community does. You can also take a middle ground, okay, and say that, okay, cold dark matter is correct, but it better be able to explain, better be able to reproduce the observational successes of lambda CDM at small scale. So the first paper which sort of argued along this line is a paper by Manoj and Michael Turner. So I'll just read this aloud. So however, any successful theory of galactic dynamics must account for Milgrom's law. We show how Milgrom's law comes about in the cold dark matter theory of structure formation. So they gave an argument for why you get this preferred scale and so on and so forth. And since then there have been many papers, including one by one of the SOC members, Asim. So Asim and Ravi Sheth wrote a beautiful paper where they did an ab initio derivation of radial acceleration relation from lambda CDM mocks. I think you were also, Tirth also produced some of these mocks. At least the mocks paper, I think Tirth was one of the authors. So anyway, so they talked about, they reproduced RAR from just adiabatic relaxation of dark matter halos from the gravitational potential wells of the baryons. Okay. Okay, so the obvious questions to ask, at least for this talk, is I'm going to take a data-driven approach. So the edifice of Mond is the radial acceleration relation, okay? So let's try to shake it, break it, test it in different dark matter dominated systems, see where it fails, where it agrees, is the scatter same, is the scatter different. So these are some of the questions which I'll try to address, just observationally point of view in this class. So basically, does radial acceleration relation hold for galaxy clusters and groups? Is the scatter as tight as those for spiral galaxies? Does it hold for elliptical galaxies? The baryonic Tully-Fisher relation, does it hold at higher redshifts? So what about baryonic Faber-Jackson relation for elliptical? So I don't have a slide on that, but I just want to make one point, and I think so Yong Tien has done a whole bunch of papers where he has looked at baryonic Faber-Jackson relation for clusters, for groups, for BCGs in clusters. There's also one point which at least I don't understand. I think in 1980s there was a paper by Stu Shapiro and his students at that time who showed that globular clusters and elliptical galaxies lie on the same baryonic Faber-Jackson relation over 8 orders of magnitude in mass. Okay, now again, globular clusters don't contain dark matter, but elliptical galaxies contain dark matter. So why should they lie on the same line? Okay, so I have not seen a good explanation, or if there is, it's just my ignorance. Okay, So then are some of these relations consistent with lambda CDM? I already showed you some, pointed some reference. So I already mentioned how you can test this using gravitational waves. So last point I won't discuss, okay? So the first thing I will talk about is, I think let's test this with galaxy clusters and galaxy groups. So we tested this with a catalog of X-ray selected galaxy clusters in hydrostatic equilibrium. So this is the Wiklinen et al. Sample. So this is just some of the data. So I'll just show you the plots. I won't go through how we did this. You can just ask me. So x-axis is the baryonic acceleration, y-axis is the total acceleration. These three plots are for galaxy clusters. This is for galaxy groups. The boundary between groups and clusters is a little bit is not sharply defined. So there's some overlap. So as you can see, unfortunately or fortunately, depending on what you want the answer to be, the points are all over the place. The relation is not very pristine, it's not very deterministic, and obviously we don't have so many points over a large dynamical range, unlike for spiral galaxies. Okay, so anyway, this is how we did the regression. So I'll just try to summarize this. This is a little bit of a busy slide. So basically what we find is that if you try to fit for A0, it is about an order of magnitude larger for galaxy clusters compared to spiral galaxies. For galaxy groups, it is somewhere in between. The intrinsic scatter for galaxy groups is much larger, 42%. For galaxy clusters, again, for some of the works it is small. I think Yongtian's analysis, where he has done the analysis using the clash weak lensing plus strong lensing sample, he gets a scatter as large as, as much as for spiral galaxies, but and there's no consensus, there's no agreement between the best fit parameters also. Okay, so RAR cannot be universal, it's likely an emergent phenomena, it does not hold for clusters, and similar conclusions are drawn from by other authors also. Okay, just in case if you think everything I did is wrong, other authors also reach similar conclusion. Their results are also all over the place. Okay, so what about elliptical galaxies? So we did this again we show baryonic acceleration versus total acceleration, and so this is the data for the elliptical galaxies, and the red one is the McGough et al. Relation, and the dashed line is the phi sigma load limit. So what we find is that it is much above the radial acceleration relation for elliptical galaxies. However, another group has also done the same analysis, Chai et al., which includes Mariangela Bernardi and Ravi Sheth. So they find that the results are consistent with spiral galaxies from the spark samples. Okay, so you can decide whom you believe. Okay, so then I think with Gauri Sharma and my student Varenya, so we also looked at, we also tried to do baryonic Telly-Fisher relation with higher redshifts. Unfortunately, I think the data has, the errors are slightly large. You have errors in both directions. So the fit is, it's actually even like there's regression in for errors in two variables is still a research in progress how to do it properly. But anyhow, once we do it, we get a slope which is slightly different from 4. Okay, so this is at high redshift between 0.6 and 2.5. So this is, I think, the KMOS sample. Okay, so how much time I have?
1 minute.
Okay, 1 minute. Okay, so what I will do, right, rather than rushing through the slides, I'll just present why this is important. I'll just flash the results and I'll just stop. Okay. So the surface density of halos, I think that is the plot which I showed, I think, of product of scale density and halo scale density and core radius, that which is constant. So beyond the test of MOND, it's also a very good laboratory for testing alternatives to cold dark matter. I think Lin and Loeb and Bondarenko showed that they use this to constrain models of SIDM. And I should also mention one more thing about SIDM. I think there's a paper by Keiichi Umetsu and his students who used radial acceleration relation of galaxy clusters to constrain some models of SIDM. Okay, so RAR can also be used as a test of SIDM, besides of course testing MOND. So Hayashi and Shiba used this to obtain a lower limit of mass of dark matter particles. So there's also a very nice paper by Andy Burkert who showed that the fact that you see a constant halo surface density automatically rules out all models of fuzzy dark matter or ultralight dark matter, okay, because there the halo surface density is not constant. The only way to get around this is obviously if you have some baryons or something, then you might obviate all these bounds, okay. Okay, so I already mentioned this is a consequence of okay. So what we did was we did the same exercise for clusters and groups, and what we find is that again the product is about 10% larger, the scatter is much larger than for galaxies, and the slight deviation from perfect scale invariance, okay. And finally we also tested this with Asim's MOX, and we find that the halo surface density is I think the scatter is slightly larger, so it's both consistent with the constant halo surface density as well as we cannot rule out dependence on as a function of mass, okay. So I think that's it.
Questions?
For galaxy clusters, what are you using to calculate the velocity profiles?
So I've not shown a baryonic telephysical. So you're asking about RAR?
Yeah, I'm asking about RAR. Yeah.
Okay, so basically just assume that the clusters are high. From the total cluster mass we get we can derive an acceleration. So
I see.
we use that. Now obviously one assumption is obviously we are assuming no hydrostatic bias. Okay, so there is that caveat in there. Okay, so that is so that's how we have done it. Okay,
You could also do it from the dynamics of
yeah,
galaxies,
so
right?
that is what Yong Tian has done. So he has
I see.
actually done a baryonic Faber-Jackson relation. But there also you can only do it at one radius. You cannot do it as a function of distance from galactic center, from the center of the galaxy cluster.
But in spectroscopic surveys, you can do a velocity
Okay.
as a function of radius, right? So you
Okay,
could
but yeah, so,
get it to
so to
larger
the
scale.
best of my knowledge, no one has done such a thing. And again, there's a little bit of a sociological problem. I asked this Andrea Bibiano, he asked Piero Rosati, and again, the problem is no one is interested in doing such a thing. Okay, so any students are there, they can do this. But anyway, so Yong Tian has done it, I think at R200 or somewhere. Okay, he has done a baryonic Faber-Jackson relation using the, I think the velocity dispersion, what you're saying, right? So we have not used the velocity dispersion. The other paper by Yong Tian using the clash sample, that is also using just the acceleration inferred from the total mass at various distances. I think there's Ranjan.
Yeah, thanks for the nice talk. I'm just still curious. It's not a physics question. Then what is it? Dark matter or MOND, according to you?
See,
You-
according to me,
You are the deciding factor in the
yeah,
universe.
okay, so one more thing I didn't mention. Okay, I mean, so nature doesn't care about what I think, but but one more thing I forgot to mention. People have also constructed modified dark matter models. I think, I mean, you know this, but Justin Curry and Lasha Berejane have proposed superfluid dark matter, and Luc Blanchet, who's very well-known name in the gravitational wave commentary. In fact, all the post-Newtonian waveforms were done by him. But he's not so well-known in the cosmology community, but he's worked on dipolar dark matter consisting of positive particles and negative mass particles that can explain the successes at small scale and large scale. But anyway, coming back to my opinion, now I think now lambda CDM simulations, again, I don't do simulations, the other experts in the room, it can reproduce RAR. Okay, so that I think Asim has been able to do it. So we need a test at very low accelerations that I think has not been done. Okay, and obviously there's the problem for MOND at cluster scale is still there. But still, it'd be foolhardy for me to ignore the successes of MOND at galactic scale. Okay, just with one line of algebra, you can explain the baryonic Tully-Fisher relation. Whereas you saw in all other talks, people are doing very complicated hydrodynamical simulations using all branches of physics. Okay, just the fact that one line of algebra, you can explain this, maybe has got to be telling. And again, I should also mention there are other theoretical underpinnings on MOND. I think there's, I mean, you know, this entropic gravity. I think recently TP Singh gave some lectures at IUCAA on what he called dark electromagnetism. Okay, so this is also a very good food for, I think, theorists or modified gravity aficionados, essentially. But I think right now, once you take into account baryons, it can explain RAR. Okay, I still don't completely understand the baryonic Faber-Jackson relation, the plot from Stu Shapiro's 1983 paper. I haven't seen a good explanation for it, but maybe it's just my ignorance.
One last.
One quick question and one comment. So one is about usual as not a MOND follower, I would make a statement that CMB observations are very difficult.
Yeah, you already mentioned that.
So that remains a big
I'm
question.
not trying to support MOND,
And
yeah.
second part is about hydro simulations. The galactic scale started to explain Steffi-McGrath's correlation of the acceleration. It's an old paper, close to 10 years now. Soon after he wrote the paper, they have shown that there is a correlation can be explained by hydro simulations. So I think.
Yes, I think there are many papers.
So which claims that so whatever they are seeing in the RAR is not a MOND effect, it's a diameter plus baryon.
Yeah, so I think Asim was able to show it. And again, there are many papers. So I think Julio Navarro had also a paper and yeah, go ahead.
Just another comment. I know that they say that it's a success in the galactic scales, but there's also this other evidence for dark matter that comes from galactic scales from the fact that you can form thin disks. And to form thin disks, you need a halo-like structure to make them stable. Has there been any discussion, or I don't follow in detail the MOND literature?
I'm not an expert, okay? I just want, so honest answer is I don't know. Maybe I think others, Ranjan or Subodhi, you might know. So anyway, I don't know.
Okay, I have a very quick question. So, a few years back, there was a paper on relativistic MOND. I mean, what is the status of that? I mean, is it applicable to galactic scales? And
So you don't need any relativistic theory to explain MOND at galactic scales, but you need some relativistic theory to explain lensing, to explain the CMB power spectrum, and also growth of structure. Okay, so for that you need relativistic theory. The first one was Bekenstein's relativistic, I think Teves. So that, as I mentioned, is ruled out by GW170817. It's also ruled out by the double binary pulsar. Okay, but I think then Skordas and Slosnik were able to reproduce the CMB. I think they were also able to get the silk damping. Okay, but again, they have to explain so many other things. Okay, so I think that is the current best. So the one word answer is yes. There are lots of relativistic theories of MOND, and I think the one by Skordas and Slosnik is the one which people are doing. But again, as I said, there are like hybrid dark matter scenarios, but that's not what you were asking, right?
No.
And again, as I said, TP Singh gave a series of lectures on, I think, dark electromagnetism, but again, I don't know anything about that. So.
okay, then let's thank the speaker. Our next speaker is Purba Mukherjee, and she will also talk about model agnostic cosmological interference with SDSS. And
Okay. Hello everyone. I'm Purba. So today I'll be presenting a recent work of ours that has been published in APJ. So the title of the presentation is Model Agnostic Cosmological Inference with SDSS for EBOS data, where we'll be probing for the simultaneously probing for both the background and the perturbed universe. So we know that the 6-parameter lambda CDM model can provide a reasonable fit to the cosmological evolution, but there are recent tensions and anomalies we are seeing with this 6-parameter configuration. Not just the Hubble tension, but different other tensions that has been the subject of this this meeting. So, to address this issue, there are generally two ways. So, either we try to look for different systematics in the data sets, or we try to find where the new physics could arise. So, to take into account the systematics, so here we are trying to probe a single survey, we take into account a single survey, the SDSS EBOS, the completed EBOS plus EBOS data, which is just a precursor to DESI, and to find out the maximum cosmological information we can find using this data set. To probe for new physics, we try to do a reconstruction in a model independent way directly from data. So, this is the basic theoretical framework. We assume a spatially flat FLRW metric to hold true at statistically large scales, and the expansion rate is given by this Hubble function. This is basically the acceleration equation. So, when we are trying to model the evolution history of the universe, what we do is we try to assume a kind of parametrization for my right hand side here of the rho, and we try to infer what scale factor or what is basically the Hubble parameter we get from here. Now, we are trying to do it in a reverse way because we have data directly of these SDSS observations which measure the radial distances given in the form of this Hubble distance, the transverse to the line of sight, the transverse co-moving distances, and the growth rate of structures from the redshift space distortions. So, taking these observations at face value, we try to reconstruct the co-moving distance, the Hubble distance, and the growth rate directly from data. For this, we employ this multi-task regression framework. So, because our data consists of observations and auto and cross correlations of these observations in the form of this matrix, we need to map these correlations or auto correlations accurately. So, we take into account kernel functions which try to map these features, and also the cross correlation. We do it in a completely Bayesian framework where we try to find out these parameters which we call as the hyperparameters of our model, and finally predict these dm, dh, and the f sigma 8 directly from this model. But with the samples we get, we can plot finally 3-dimensional phase portraits of the reconstructed functions at each of these individual redshifts. So, these are basically the 6 effective redshifts, the SDSS BO plus RSD data probe, and we can find that we get a volume where shown in blue. So, so this is basically the volume our reconstruction gives us. So, this is basically a force portrait kind of a thing. Now, in this phase portrait, if we take the Planck lambda CDM chains and if we try to superimpose it in this figure, so this is shown with this red region, red ellipses. So, in the very low redshift, so the plot is shown with the within the 2 sigma confidence level. So, in the very low redshifts, we see that up to 0.68, so our results are consistent with Planck lambda CDM for both the background and the perturbation sector. So, I am talking about linear perturbation sector. But at 1.48, we see that the 2 volumes do not coincide. So, there is some inconsistency we are finding. So, data is trying to tell us between what the reconstruction gives versus the Planck lambda CDM predictions. And we also find a similar kind of an inconsistency at the higher redshift 2.33, where the Lyman alpha BO data is there. So, now let us interpolate it at the as a function of redshifts. So, this is basically the profile of dm by rd, this is dh by rd, and this is the f sigma 8. So, in the very low redshifts, we see that the Planck lambda reconstruction which is shown in blue is consistent with the Planck lambda CDM predictions. But at very high redshifts, at the 2.33 Lyman alpha point, so there is an inconsistency with Planck lambda CDM which exceeds 2 sigma. A similar nature is also found in the DHRD profile, where we again find a more than 2 sigma inconsistency at 2 sigma, which exceeds 2 sigma. For the f sigma 8 data, so we do not have any data point at this high redshift. So, the redshift we have the highest redshift the F sigma 8 data can probe is the 1.48, the quasar data, and we find that there is a more than 2 sigma discrepancy at the F sigma 8 measurement at this redshift. So, we can summarize our findings as that at these low redshifts, we find good agreement between reconstruction and the lambda CDM predictions. At higher redshifts, there are deviations from Planck lambda CDM. At z equals to 1.48, the Lyman alpha, the quasar data, we find the deviation in the F sigma 8 to be more prominent. But then at the Lyman alpha data, there are anomalies we observe in the DMRD and DHRD. Now, what happens if we try to map each of these volumes to the lambda CDM model? So, assuming lambda CDM is my cosmological model, what happens if I try to fit the model to each of these volumes? These are the plots. So, in this, here is basically the H naught RD, this is sigma 8 and this is my omega m. So, in the first 4 effective redshifts, we see that the correlation between these parameters also remaining same, and the Planck lambda CDM model is coinciding with our reconstructed volumes. But at z equals to 1.48, where the quasar data is present, we find that there is a switch in the correlation. So, the direction of this correlation between these 3 parameters changes. At 2.33, we also observe that there is a discrepancy with what our reconstruction gives with Planck lambda CDM. So, we can draw a tension heat map for these cosmological parameters. So, this is for this is a heat map that shows the tension between each of these effective redshifts compared to Planck and also the SDSS lambda CDM predictions. So, we find that for H naught RT, the tension is at around 2 to 2.5 sigma at the Lyman alpha data point. Tension is omega exceeds 3 sigma for the Lyman alpha data point, and for the sigma 8, the tension is like 2 to 2.5 sigma tension at 1.48 redshift with the remaining data point. Now, we can draw a whisker plot showing the trends in these parameters. So, because BO data can give us predictions of our H naught RD, we can take RD, we can calibrate RD to the Planck value, and then we can draw, predict H naught from there. Now, interestingly, if you look into the profile of this DHRD, the y-intercept of this figure gives a value, will lead to a value of H naught RD, which is close to 100. That if we inject the H RD from the Planck there, we arrive at a H naught that is close to 68, which includes both Planck and Schu's H naught within the 2 sigma confidence level. So, these are the trends we observe for each of these individual redshifts. So, at z equals to 0.15 to 1.48, so we see that there is an increasing trend in H naught. So, H naught is closer to the Schu's value, and then it closely goes to the Planck value as the redshift increases. If we compare this with the for the omega m, we see that the omega m is mostly consistent. Constant value of omega m is mostly consistent within the 1 sigma. However, there is this slightly increase in the mean values of this omega m. For sigma 8, we find that up to 0.7, the sigma 8 value is consistent with Planck lambda CDM within the 1 sigma. However, at 1.48, we find that this is in more than 3 sigma tension. Similarly, for the S8, we find there is also a statistical tension at 1.48 redshift for the S8 data in our reconstruction case. Now, what happens if we compare this with more future observations? So, SRG rosita act DR6 Planck with Planck PR4 act DR6 plus Planck PR4 when cross correlated with DESI and also the DESI full shape data. So, when we compare the H naught constraints with the DESI full shape data, we observe an oscillating kind of a pattern. So, where the lower redshift values are lying midway between Planck and Schu's, then there is a sudden increase in the value of H naught, and then H naught is coming closer to the Planck values. For S8, we observe a similar kind of trend we find in the SDSS data. that at 1.48 we find 1.49 we find that there is again this tension between what Planck predicts and that is which is in more than 2 sigma tension. Also, a similar kind of effective increasing in redshift is found in SI, but in all the 3 cases we find that there is an oscillating pattern. For the ACT DR6 cross-correlated with DC, we find that there is always an effective increase in these values, and this is most prominent in the parameter S8. For the SRG erosita, the trends are similar, but this happens at a different kind of a redshift region. So, this kind of a trends in the cosmological parameter shows lambda CDM needs modifications, and this is clearly visible from just one survey, the SDSS BOSS, SDSS EBOSS. Now, with new data, the DESI data coming, so if we look at the DESI data at hand, we can find that at the lower redshifts, we find that there are deviations from Planck lambda CDM as shown in the DESI data. So, and if we plot the equation of state, we observe this kind of a feature in the data set. So, if we try to do our analysis on the DESI full shape data, we will be probing, and if you try to probe this reconstructed phase volumes, so we will find that the correlations to change in between. So, the nature of change in correlation which has been observed here, it will become more prominent at these redshift. So, this framework can be used as a diagnostic tool to test beyond lambda CDM physics at for the next generation future DES 5-year data and also the upcoming Euclid data. And interestingly, this framework can be written as an autonomous system, which has been already shown by Charvan et al. And so our framework will provide a model independent template for extracting the maximum cosmological information from a single survey, simultaneously for the background and the perturbation sector, which accounts for both autocorrelations and cross-correlations between different observables. So, this will offer a robust benchmark for stress testing lambda CDM, and which can be useful for future observations. Thank you.
Thanks, Purva, for finishing within time. Questions? Questions, comments?
Thanks for a nice talk, Purva. Can you please go back to the Whisker plots? Yeah. So, if I understand correctly, for say H naught, at around z equals 1.49, the error bars are relatively large. And for omega matter not, like for z equals 0.15, the error bars are large. And consequently, for S8 also, the sigma 8 and S8, they are also large. So how do you interpret this? I mean, like,
Okay, so this
is it a good thing or a bad thing? That's the question.
So this is basically the limitation because of the data we have. So for the SDSS, the BOSS plus EBOSS data, so we have DVRD measurements. So we do not have measurements of DMRD, DHRD simultaneously. So there is kind of a loss of information when we try to project it in our phase portrait. The only observation we have directly is for the F sigma E. So this causes this increase in the error bars at the lower redshifts. For the 1.48, so the maximum data for the F sigma 8 we have is for the 1.48. After that, our reconstruction basically is unable to account for the features at higher redshifts. So now when we are trying to model the lambda CDM based on these phase portraited, so at these extreme boundaries we are finding these errors are becoming errors are shooting. So, but with the recent DESI data, because the data is not yet publicly released, but then they have a complete information of all these observables together, so then that can be tested.
Any further comments or questions? If not, let's thank the speaker.
Thank you.
Our last speaker for this session is Tunima Duwari, and she will talk about a dark energy model under thermodynamic scrutiny.
Good afternoon, everyone. I am Tanima. I want to thank the organizer for giving me this opportunity to present my work here. Today, I am going to talk about thermodynamic analysis of a dark energy model in thermodynamic phase transition. This presentation is based on this article, and this work is done in collaboration with Professor Narayan Banerjee and Dr. Anand Dasgupta. The motivation of our work is to say the thermodynamic viability of a cosmological model that gives rise to a late time cosmic acceleration via the generalized second law of thermodynamics. And then next we want to check if this model is thermodynamically stable or not. So at first we consider this spatially flat FRW metric where this AT is the scale factor, and we consider an answer on the scale factor that the scale factor varies as sine hyperbolic t to the power 2/3. This answer is tailored to imitate the characteristics inherent to lambda CDM model, that in matter dominated era the scale factor varies as t to the power 2/3, and in lambda dominated era the scale factor varies exponentially. So we consider the present value of the scale factor to be 1 and this T0 also to be 1. So we want our cosmological parameters as well as our thermodynamic parameters in terms of redshift. So we define redshift and then we write the cosmic time in terms of redshift. Then we calculate the Hubble parameter. We define Hubble parameter as A dot by A, and throughout my presentation this over dot implies that this is the time derivative of the quantity. So we calculate the Hubble parameter in terms of redshift, and then we define the deceleration parameter in terms of redshift. So when we plot the deceleration parameter as a function of z, we find that sign at this redshift value. This implies that the expansion of our universe goes from decelerated phase to accelerated phase at the value of redshift around 0.4 for our model. Next, for thermodynamic analysis, we consider the dynamical apparent horizon instead of the event horizon. So the horizon entropy is the entropy of the dynamical apparent horizon, and in spatially flat FRW metric the radius of the apparent horizon goes as 1 over Hubble parameter. From that we can calculate the area and the volume of the apparent horizon as this, and given the entropy of the apparent horizon as 2 pi a in the unit of 8 pi g equals to 1, we can calculate the rate of change of horizon entropy in terms of Hubble parameter and its time derivative. So next we consider that the fluid inside the horizon is in thermal equilibrium with the horizon itself. So now the question is this assumption valid? So Mimoso and Diego showed that the thermodynamic equilibrium with the thermodynamic equilibrium between the radiation and the cosmic horizon cannot be achieved. This limitation arises due to Wien's law because this ensures that the typical wavelength of the radiation is consistently larger than the horizon radius. But for non-relativistic particles, this thermodynamic equilibrium can be achieved, and when we consider that thermodynamic equilibrium between the dark energy component and the horizon, it is also consistent, and in our work we do not include a radiation component. So therefore our assumption for the thermodynamic equilibrium between the horizon and the cosmic fluid is valid. So our next task is to choose the temperature carefully, because in static scenario we know that the temperature is given by the surface gravity over 2 pi, and where the surface gravity is defined through the time-like killing vector. But in dynamical situation where the cases are characterized by dynamical situation, this faces these challenges due to absence of the time-like killing vector. Now, Hayward proposed an alternative definition of surface gravity, where this is valid for dynamical situation for spherical symmetry cases through this Kodama vector, where this within spherical symmetry this Kodama vector actually successfully replaces the killing vector in an evolving system. This is the definitions of Kodama vector, where this capital R is the areal radius and epsilon b is the volume of the two sphere of the two metric HAB. So, therefore, Hayward's concept for surface gravity is defined by this, where this kappa is this surface gravity related to Kodama vector. Then for spatially flat FRW cosmology, this this surface gravity is given by this expression, and from that we find the temperature as the surface gravity over 2 pi, which is given by this expression. Now, it is to be noted that when we put H dot equals to 0, that is in case of static situation, it gives back to our Hawking temperature. So, now at equilibrium the temperature of both the horizon and the fluid is given by the Hayward-Kodama temperature. Next, we apply the first law of thermodynamics to the fluid inside the horizon, and then these are the field equation in the unit of 8 pi g equals to 1, where rho and p are the total energy density and pressure of the matter content. So, from this we can find out the rate of change of entropy inside the fluid, where in the second equation I have incorporated these field equations here, and then incorporating the Hayward-Kodama temperature we arrive at this final expression. Next, to calculate the total entropy, rate of change of total entropy, we sum over this expression with the rate of change of horizon entropy to find out this expression. So, next our task is to check whether our model is thermodynamically viable or not through GSL. So, according to this generalized second law of thermodynamics, the total entropy of the universe cannot decrease. So, this S total dot is always should be greater than 0. So, when we plot this for our model, we see that S dot is always remains positive. Therefore, we can conclude that our model follows the generalized second law of thermodynamics. Hence, our model is thermodynamically viable model. Our next task is to check whether this model is thermodynamically stable or not. To check this thermodynamic stability, the entropy of the fluid inside the horizon has to be maximized. So, this Hessian matrix of this entropy should be negative semi-definite, and from these conditions we get that these two conditions should be satisfied simultaneously in order to achieve this thermodynamic stability. In the first condition depends on the specific heat at constant volume, where the second condition, which is denoted by alpha, is dependent on specific heat as well as the isothermal compressibility. So, we need to find out these two thermodynamic parameters. So, we calculate CV in terms of redshift and beta T, that is isothermal compressibility, in terms of redshift. And when we plot these two conditions side by side, we see that for the range of redshift where this first condition is satisfied, this violates the second conditions, and when for the range of redshift where the second condition is satisfied, it violates the first condition. Therefore, these two conditions are not satisfied simultaneously. Therefore, our model is not thermodynamically stable. But when we plot the specific heat capacity at constant volume, we find an interesting result, that CV shows discontinuity at a particular value of redshift. This is exactly where the Q flips its sign, which means that the the expansion of the universe, when goes from decelerated to accelerated phase, it shows a thermodynamic phase transition. And we have checked that there is no discontinuity in the first order derivative of the entropy. Therefore, it is a second order phase transition, and the order parameter is the deceleration parameter. Here is the summary of my talk. So, thank you.
Thank you. Any question?
To calculate the Hessian matrix in order to check the thermodynamic stability, why don't you consider the total entropy? You just consider the matter fields entropy.
Yes.
Why don't you consider the total entropy?
Because we want to check this fluid is thermodynamically stable or not the.
No, I think the system is, there are two systems, right? Matter field plus horizon. So you need to check the whole system is stable or not.
Okay.
I mean, that's my opinion. You can think of that. If you take the total entropy, it may be thermodynamically stable, maybe.
But there is one catch when actually there is one article that is Cosmographic Study of Universe's Heat Capacity by Luongo, where he showed that when to posit it is necessary to consider CV to be negative when universe is universe goes in accelerated expansion. And from this you can see that when CV is negative, if CB is negative, that will always give rise to this violation of this first condition.
No, that is only with SE, that is only with matter fields entropy. I am talking
No,
about
I mean, no, if we consider also the total entropy, the CV will also be, this is the general form, right? Here we have not considered any model or anything. So, this is always minus 1 over T square CB. When in accelerated expansion, if CB is negative, that means this term will become positive. So, this will violate this first condition. So, this will in accelerated expansion, this will, if CV goes negative, then it will always violate this condition.
Okay.
Any other question? If not, let's thank all the speakers of this session. Is it tea time? Where is Tiraj? Oh, there is a poster station at 4:30. From 4:30 where? Just outside. Okay. Okay.